So yeah, the first question is really straightforward. The second is a little bit tricky, but it's not so difficult. You may need to find an approximate answer. It may be a difficult mathematical equation because this is not like the both of the sequence lengths are not given. It's like we are given the length of one of the sequences, and our goal is the other sequence. What is its expected length if we are going to find its in its entirety in the other sequence. All right, so one of them is like a small sequence, the other is large. So B here is going to be your small, shorter sequence, shorter length sequence. And what is the expected length of B so that we find it with all matches inside A. All right, so again, you're going to set that expected value to 1 and form the equation and try to find the length of B. That's your variable, and that will be the only unknown in this equation. So you have to form an equation in which the length of B is the only unknown in this equation, but it's going to maybe appear, it's not going to be easy to solve this equation directly, but you may try different things. If you cannot solve it with a really single close formula, you can try numerical methods like try to approximate the length of B by trying different values. For example, what happens, for example, if the length of B is like 20, what is the expected value of that? It will be easier to compute. Instead of setting expected value 1. So you may play with the length of B one by one to get closer to the value of 1. And you may just stop there if you get close enough. So, I mean, I'm not looking for in problem 2, I'm not looking for an exact answer. So if you approximate the actual integer value and you just report an integer value here, that will be fine. All right, but yeah, I gave lots of hints actually, so it will be really simple to do both. But it will be a nice exercise to see on statistical significance of alignments and also on the dynamic programming solution that we have talked about. All right, so that's the goal of this assignment. Any questions from the assignment? Okay, so today the plan is to go over the statistical significance of alignments and finish it. There are really nice additional readings about this, and this one on the course website, the Statistical Significance of Alignments, Chapter 3 from a reference book. So assessing the significance of sequence alignments, I suggest you read this. It provides a nice historical background too on how people have developed, researchers develop these formulas. And there are different formulas. This is some of the formulas that we have seen, like this one I'm going to show you. So this one was Carlin and Altschul's formula, which I'm going to show you next. But there are similar formulas to that, which are actually different. This is not, they're using, so this is still the length of the longest run, matching run, maybe including mismatch too. If there are mismatches, there should be an additional term in this formula. So you don't need to memorize these formulas, but I just suggest, and some of them they look really complex. But this article, I mean, this chapter provides a nice historical background on how these formulas have been derived, how different formulas have been proposed by, for example, Carlin and Altschul in 1990 proposed this. Lambda roughly equal to this one. And this P actually is closely related to the scoring matrices. Today I'm going to talk about what this lambda is and how it's used in BLAST. So, and yeah, by using this, Carlin and Altschul developed it into a score, and assessing the statistical significance with of alignments with gaps is also difficult. This chapter also talks about that, and it talks about a certain distribution, which is the Gumbel extreme value distribution, which is the scoring distribution the distribution of scores of alignments between random sequences. They look like this distribution actually. First, researchers thought that it's normal distributed. I mean, if you just take random sequences and align them, you will get scores normally distributed around some negative value. Because the expected value of a random match is when it's negative, you would expect the total alignment is going to be normally distributed around that region. But then they found out that it's not like that. It has a different shape actually. This looks like normal at first glance, but actually, as you can see, it's right skewed. There are more positive values to the right of this. So you're likely to get some positive values for random gaps, which means that you cannot assume normal distribution. But by using some of these you don't need to understand everything written on this chapter, but it will give you a nice insight as to how statistical significance of alignments are computed. And there's another short chapter. This is like 4 pages only. Significance of alignments, and it also shows that it's right skewed. And they computed a different score, the z-score, instead of the expectation e-value like BLAST does. In this paper, it shows how we can compute a z-score as a normalized deviation of a score from the mean. Okay, so I'm going to talk about the z-score also today, or maybe p-value. I'm going to, and how to compute the p-value, which is the probability. But yeah, that's the plan of today. We are going to finish this in the first hour, the statistical significance of alignments, and then I'm going to start the new chapter, which is suffix trees, and it's a data structure which allows us to perform exact small pattern searches in a very long strings very fast after you index your long genome by using and build a suffix tree out of it. So it's a really nice, and this you're going to see a way to pre-process a large genome, and that suffix tree is going to be our index structure. So when we have such an index structure, you're going to see how exact pattern matches can be reduced to a very, they can be made very, very fast, linear on the size of your pattern. So this is really like something impossible, right? I mean, it's like, imagine you have a large book like this, and you're looking for a keyword in this book, whether a certain keyword exists in this book. We are usually given indices. The index at the end of a book tells us whether a keyword, in which pages that keyword occurs, right? Imagine you want to have a dynamic index in which you're trying to look for any pattern that the user gives in a book. If you don't pre-process and index the book, provide a digital index like this suffix tree of this book in the first place, the best you can do is just linear scan, right? You cannot do better than linear scan. You have a pattern that you're looking for. For example, you're looking for this pattern, maybe dynamic programming. So 2 words, dynamic programming. And you're looking for where that dynamic programming word exists in that 1,000-page book. The best you can do is write a program to quickly, linearly scan that book. From the beginning, you're just going to try to match a window of characters to this keyword dynamic programming, and you're going to do that continuously until you reach all the way to the end. If you're looking for all of the occurrences, if you're looking for the first occurrence, still you have to, on the average, you have to still go half of the book on the average. So, which means it's linear on the size of the book. Now, With a data structure like suffix tree, you will be able to answer such queries whether the keyword dynamic programming exists in the book or not, with time proportional to the length of the pattern. Okay, so for example, dynamic programming only has like 15 words. In 15 steps, you'll be able to figure out whether, and regardless of the size of your book, it may be a 1,000 page book, 10,000 page book, 100,000 page material. You'll be able to still find the occurrence of dynamic programming in time proportional to the length of your pattern, which is very fast. Regardless of your database size, you will be finding you'll be answering these queries very, very fast because the queries are usually short. Okay, so that's we are going to see such an index structure after we talked about this statistical significance of alignments. And of course, you'll have to pay a cost for that. This magical, very fast computational complexity doesn't come for free. But so you'll have to spend some time to index the entire book. We may, in suffix trees, for example, there are methods to index the entire book in linear time of the size of the book, which means that it's like if you're just going to perform this query once, there is no need to build the suffix tree because you're already spending the same time as the linear scan. But if you're going to be performing these queries a lot in the long run, just spending this linear cost of the size of the book once is going to be our pre-processing or index building stage. For which we actually we are just going to do it once if the book doesn't change from time to time. If it's like a static genome, a reference genome that we're working on, we're going to do this only once. And then whenever we have a query, we are going to be answering these queries very fast. So that's we are going to see that index structure. So let's go ahead and talk about the statistical significance of alignments. If you remember, the simple formula we had was this. The expected length of an alignment of length L, of a matching run of length L between two genomic or protein sequences of length M and N each is whatever the probability of a single match. So we take L to the power of that single match. In case of DNA sequences, P here is 0.25 or 1/4 if they are or equally, if the observing each DNA nucleotides are equally probable. And in the case of protein sequences, it's 1/20, but we know that it's not that assumption for proteins, assuming that all the amino acids are equally likely to be observed, is a very bad assumption because it's, in nature, some amino acids are really rare and some amino acids are seen a lot. So they are not at equilibrium. So therefore, this assumption of using a constant P doesn't work for protein sequences. But the idea is, as the length of the sequences get longer, quadratically, for example, if they're all both equal length, this will be like n squared P to the L. And this is the expectation value of a particular L. The expected length of the longest match, on the other hand, can be approximated as by setting this left-hand part to 1, because it's like we expect to observe it at least once. It's something like that expectation is once. So it means that expected value once, when you observe such a length of matching run, you're not surprised. 1 is something that we observe once. So it's like, therefore, we set the left-hand side to 1 and solve for L by taking the logarithm of both sides, and then it becomes the longest run is log 1/P M times N. So in other words, if M and R again are equal, we can take this N squared, but it's 2 times the logarithm of the length of these sequences. You can also say that if they are of equal length. So these were some examples we talked about, and Carlin and Altschul and other researchers too. In 1980s, one of the biggest developments in sequence alignment was the computation of the statistics of statistical significance of sequence alignments. And Carlin and Altschul and other researchers, they came up with different solutions for this. And here is what Carlin and Altschul produce. Let me show this one and let me start annotate. So this is the formula that they've come up with. They said the expected value of to obtain a score larger than or equal to some raw score. So this is the raw score of our alignment. So given the only thing that we get out of this local alignment we have is this X, the alignment score. And all the other things, this M and N are actually, I mean, N is like the query size that can be very small compared to the database size. M, it can also be even ignored. For example, in M, we are going to have 100 billion nucleotides length of database, where n is just 1000. In that case, this is this, but you're actually multiply this quadratically, so n shouldn't be ignored in this case. So you probably put your query length also into account because you multiply your database size with it. So that's also something that's given as input, but this one is a parameter of the database, if or vice versa. If m is your query size, n will be the size of your database. But x is your score, and by using this one basically tells that if as your database grows, your expected value grows linearly with the database size. If your database size doubles, you have twice more sequences compared to last year. You will have larger expected values. And if you get also a larger row score x, this will also decrease your expected value by a logarithm by a factor of 1 over e to the power that. So it's like this e to the minus lambda x is 1 over e to the 1 over e to the lambda x, and therefore as x gets larger, your e value is going to get smaller logarithmically. All right, so this is what you should get out of this equation. And the only thing that I'm going to discuss here in more detail is what is this lambda? And this lambda, we started talking about this the last time, and we said that it's closely related to the scoring matrix used. So for different scoring matrices, different lambda values are used. This is just a constant for that, for a specific scoring matrix. And in order to understand how it's computed, we had to look at what the scores in scoring matrices mean. So originally, our match and mismatch scores are actually log odds ratios, meaning that when you have a pair of amino acids, what is the likelihood that they are going to be observed together in the same position of different proteins? So what is the likelihood that we observe those two together in an alignment? Like, what is the probability to observe F and Y together in an alignment? So compared to a random matching of those two, so when we just randomly mismatch two different amino acids with a random alignment, you will have random mismatches. Okay, so the probability of a random mismatch of two amino acids is basically this pi times pj. If pi is the the frequency of that amino acid in nature, if amino acid I, and if pj is the frequency of amino acid type J in nature, if the probability of randomly matching these two specific types of amino acids in a column is pi times pj. So this is like the probability of their random matching. And qij is the frequency that we actually observe them, these two types of amino acids in the same column in an alignment. So this qij is found by looking at manual alignments like this and computing a frequency where they two are observed together. And this ratio, which we call the log odds ratio, this is like if these were like probabilities, we are taking the ratio of two probabilities. It's like a likelihood. Log, sometimes this is also called log likelihood. Tells you that if the likelihood here is a positive number, when you take not a positive, not they will always be positive, right? They cannot, this ratio can never be negative, because these are frequencies. Frequencies are the smallest the frequency can get is 0, and the largest 1. So Qij is going to be the largest value of Qij, so is going to be 1, and smallest 1. So both of these Qij, Pijs, they are values between zeros and ones, and their ratio is always going to be positive. But we're going to compare this ratio by comparing these two values, whether Qij is larger than this, whether it's more likely to observe these two amino acids together in nature more compared to random matching of them. So that's the number, therefore we are comparing, our threshold is 1. And logarithm of 1 is 0, which means that if they're equally likely observed, we don't have a match or mismatch, positive or negative score, it's just 0, okay? But if they're more observed together in alignments compared to random matching, it means that we need to give them a match score, because in alignments they're observed more. So we should guide the other alignments in such a way that these are matched together. So one way to do that is to give them a positive score. So if Qij is larger than this one, the logarithm will be a positive value. And similarly, if Qij is less than Pij, the logarithm will be a negative value. These will be our match and mismatch scores and penalties. And this is Sij is this row score, which are the logos ratios. Okay. Now, if you look at any Blossom 62 PEM, or PEM matrices like this, you're going to see that they do not look like log likelihoods. They are some integers. So what happened is that this Sij was actually multiplied with a number to get the integer numbers that we see here. So this example also shows what that log likelihood means. So this is the sentence that I wanted to say. Scoring matrices are usually provided as integer matrices. The original log likelihoods ratios, which may be all very close to each other. So, for example, you will have match scores that are not inflated. For example, 1.1, 1.3, 1.5. So the differences will be like that for even positively matching. More likelihood to observe pairs of amino acids, we will have scores like that. So they're actually scaled by a constant factor. And lambda is approximately inverse of the original scaling factor. So they're like multiplied by 1 over lambda. If lambda is a number less than 1, for example, if lambda is 0.1, it means that all the values, original log likelihood values, are multiplied by 10. Okay, if they're all multiplied by 10, in that case lambda is going to be 0.1, 1 over 10. Okay, so this is how they defined lambda. Okay, so in other words, this one, so they multiply. So this score actually here is the original integer score we have in our Blossom 62 matrices. So the log likelihood multiplied by 1 over lambda gives Sij. In other words, we have this equation here. Let me again use this annotate. Look at this. So this is this Sij is the integer score in the Blossom 62. The log likelihood is multiplied by 1 over lambda to get this integer score. And from this, you can take both sides, you can take e to the power of both sides, and you're going to get Qij is equal to Pi times Pj e to the lambda Sij. So all the Sijs are known. Our goal from here is to figure out what lambda is for a given scoring matrix values Sij. So when we are given a Blossom 62 or PAM matrix, we know the Sijs. We also know what Pi and Pjs are in nature. The amino acid propensities or frequencies are probably well established. So let's amino acid frequencies in nature. For example, in human proteins or in nature, let's look at in nature. So yeah, here as you can see, there are lots of results. And if you look at this one, let me zoom in on this website. They looked at the observed frequency in vertebrates. Okay, and as you can see, some of them, 1/20 is 5%, right? If they were all equally likely, we would all see 5%, 5% each. But some of them are like serine is observed more. But tryptophan, that W 1.3. Look at the difference, like almost 8 times more frequently observed. Serine is more frequently observed than tryptophan. Valine also larger than 5%. Some of them are above the equal frequency of 5%, and some of them are below, as you can see. And so that PI/PJ values in the on the slides, they are these values. So here the PA, for example, for alanine, it's going to be 0.074. 0.074 is 7.4%. These are those PI/PJ values. So we know what PI/PJ is by looking at, by observing all the sequences we have. What we don't know is QIJ. We don't have the alignment. So QIJ is not known in this equation. Okay, for all the amino acid pairs, for example, we either need to go back and look at the original papers of Dehov et al. To see what QIJ values they have obtained. But in order to obtain this QIJ, we need to look at a lot of alignments. So it's easy to compute these statistics. Sorry, this one. It's easy to compute these statistics per individual amino acids. But what is the occurrence of, for example, asparagine and aspartic acid together in alignments? How do we compute that QIJ or approximate that QIJ? We need to look at lots of manual alignments and see in how many of them those two amino acids together compared to all possible pairings of these amino acids. So this is difficult to compute, and in those 1983 paper, this is what Dehov et al. Did. But what we know is that this is a probability distribution over pairs of amino acids. So the summation should be 1. Okay? So what we can do is we can just set, if we just sum over all possible pairs of amino acids, this right-hand side, since these are QIJs, we can set the summation to 1 so that the unknown of QIJ is removed from this equation. Everything in this equation is known. We know what PI/PJs are, those individual amino acid frequencies in the table. Sij are the scores in our scoring table. The only thing unknown in this summation is lambda. And we've tried to solve this equation numerically to find what lambda is. So we can estimate what lambda is. This is a difficult formula to solve it just in one shot, but we can estimate what lambda is because that's the only unknown in this equation. All right, so this is how lambda is computed. And as I said, this was an analysis. The original initial analysis by Carlin and Altschul was only for alignments with no gaps. Analyzing the statistical significance of alignments with gaps was difficult, but they did that empirically by looking at the distributions of random alignments. So that's one way to measure the statistical significance is to have your to estimate your background distribution of random alignment scores by generating lots of random alignments, like taking samples from the entire universe of random alignments. Uh, so, and if you look at the histogram, for example, so this is the green one here is the normal distribution, and the red one, which is right skewed, as you can see here, is the extreme value distribution. It has a very nice formula for its probability density function. Okay, so there's a question before moving forward. I'll try to answer Serjan's question, which is what is Qij here in the previous slides? Okay, so Qij is the observed frequency of two amino acids of type I and J together in multiple alignments, in alignment. So what it means is that it's the likelihood to substitute amino acid type I to type J in different organisms' proteins. This is what Qij is. Okay, so it has two indices. For example, when I say what is QIL, okay, so Q, if this I is the specific amino acid isoleucine and J is leucine, okay, what is QIL? When I say that, what I mean is that what is the probability? So Qij, you can consider this as a probability of substituting I with J. Okay, that probability is difficult to compute because we don't know how evolution works in reality. I mean, we don't have the entire universe. We can just estimate this. Okay, we can just estimate what is the probability to substitute leucine with an isoleucine in a protein of one organism, and when we observe the same homolog protein in another organism, what is the probability that this position, this isoleucine, will be a leucine? It's what is this? This is what actually Qij is. It's a probability. So since we cannot compute it, we don't know its real value. We can approximate it. We can try to estimate it by looking at actual examples in nature. So this is what they did to estimate the Qijs. This is what they told it in 1983, in 1980s. So if you go on to look at a specific example, you have to look at this alignment. Okay, so imagine we want to estimate Qij from this table. Okay, so imagine this is the entire this multiple alignment is the entire set of proteins we know in nature right now. By just using this, the things that you see here, how can you estimate Qij? Also estimate Pi and Pj. For example, what is Pi and PL? If you're looking for here, for example, QIL, okay, and you need to also find what Pi and PL are. These are their individual occurrence probabilities. We could also refer to the table that I showed you on the web for these, but imagine this is the only thing we know about the protein universe. And these are proteins from different organisms, or they may be paralogs within the same organism, but these are different protein sequences that we know that they're homologs. Okay, so in nature, for example, one of them is substituted, so L is substituted with V. In the same protein sequence, L is changed to V. This L is changed to, and L is changed to K. So these are all pairs of, looking at a single column here, focusing on a single column here, all pairs of amino acids in this column tell you how many times they appear together. All right? So how do you figure out what Pi is? Count how many amino acids you have here. Count all of them. 1, 2, 3, 4, 5, 6, 7, 8, for all of them. So count all individual amino acids. How many of them are I's? That ratio is Pi. How many of them are L's compared to all of the amino acids here? That ratio is L. So Pi times PL is the probability that we are going to observe them together. Okay, so what is QIL then? QIL, you count in a column how many times you observe I and L together in a column. Okay, maybe 0 in this example. No, it's not 0. There is one INL. Okay, so IL, 1. Another IL, 2, 3. And 1, 2, 3. In the single column, let me undo the last thing. If you look at this column, I observe the IL pairing 6 times. Okay, 2 I's and 3 L's. Their possible pairing is 2 times 3. I observe I and L together 6 times. You do this counting for the entire columns, entire and multiple alignment for all of the columns. And that count over all possible pairs of amino acids will be your QIL. So the ratio here again will be a frequency of the counts of ILs together over all possible pairs. How many possible pairs you have in this? For example, if there are K sequences here, and imagine these gaps were not there. If we have an ungapped alignment here, for each column, I will have K choose 2 pairings of amino acids. So K choose 2 times N, which is the length of the alignment, will be what you're going to be writing in this denominator. Okay, so QIL basically is the observed frequency of 2 amino acid types together in nature, their substitution probability. So, and the ratio of this over pi times pl, which is if we just randomly produce an alignment, which we put these two I and L together in an alignment randomly, that will be the probability to observe these 2 types of amino acids randomly in that column. It's just taking 2 amino acid types from the bag. So the ratio of this to this is our log odds ratio. Okay, so you can also, if this is not clear, I suggest you read these additional readings on the course website, and it will help you to understand how they are computed. Also, you can directly refer to the original paper of Dayhoff et al. They are probably also describing it there also. Okay, but I mean, I'm not specifically saying this to you. Anybody who feels some difficulties here, please read the papers by Dayhoff et al. Or these chapters to get a better understanding of these. All right. So when we have gaps, as I said, what we can do is, so in any case, actually, I'm going to show you before the break, I'm also going to describe a different problem, not about the statistical significance of alignments, statistical significance of any result. So you're looking for something, your algorithm finds something from a universe of some solutions, and your goal, what you want to ask is, what is the let me put here so you can see my face when I'm talking. Okay. What is the likelihood of observing? Is this result a good result? Imagine you have an algorithm and you say, I have found this. I have a data mining algorithm, and this is the data I mined. If you give this result to somebody, how do you figure out your algorithm is actually producing something good? What if I randomly produce some solution and say, oh, here's the thing I found. Okay, so if this randomly producing something and giving it as a result, obviously should be bad, right? I mean, anybody could find that. So in that case, the other algorithm has no utility at all. What it had found could be found randomly by just picking things from the data randomly. So we need to, in order to give some value to the utility of an algorithm or the alignments that we have found, for example, in order to give a meaning to them, this alignment that we have found is different from random. So that's statistical significance, and it's really important to compute them nicely. Here, in local alignments with gaps, what we see here are some experiments to get this is also called sometimes the null distribution, the background distribution of random alignments. This is our null distribution, and we are doing a hypothesis test here. Actually, we are saying the score that I observed here is equal to is coming from the null distribution, which means that the score you see here is from two different random sequences. If we can reject this null hypothesis, saying that, oh no, this score that you observe here is very unlikely to be observed from this background distribution. For example, if you get if we are using this gap opening penalty of 12, maybe these are scores between two sequences of length 1000 each, and these are our frequencies, and these are our score values, which are all positive, as you can see. Between random alignments, we can obtain positive scores. But if somebody comes up and says that I found an alignment in which my score is 200, look at this distribution. This is the distribution of random alignments. If somebody comes and says that I found an alignment with a positive score of 200, you're going to say that this alignment, the score of 200, is unlikely to be coming from this distribution. That's basically, you're saying it's statistically significant. All right. So this is exact, and you may quantify that. How unlikely? Then you say 200. How unlikely it is coming from this distribution? You can give it a p-value or a z-score. The probability to obtain a score of 200 or more, if you know the probability density function of this null distribution, you can compute the p value actually. My internet connection seems to be stable, so if you have any difficulties in terms of sound and video, it may be O2's internet connection to outside world. But anyway, I'm still recording locally, so you'll be able to watch the other parts. Okay, so let me check my internet speed test. So let's see whether it's something on my machine. Okay, I think my internet connection seems to be very fast, as you can see, since I'm on the local, but it may be O2's outside connection. All right. Yeah, actually, I think there's something wrong with Cisco, or maybe, yeah. And, all right. Okay, I will continue this. The parts that you miss, I hope you'll be able to watch it offline later from those YouTube videos. All right, so I'm going to continue this. So basically, we need to, in order for generic statistical significance computations, we need to first construct a null distribution and see how different the score we get is from this null distribution. And yeah, okay, it's refreshed now. It's fine. Great. I think it was something about Cisco, or I don't know. Pre-computed lambda and k values are used for different scoring matrices and gap penalties in blast queries. They first convert the row score to a bit score. Then the e-value is computed by multiplying this bit score we have to this. So bit score means that they use log base 2, not it's like a conversion from the log base e to log base 2. And FASTA also tries to use this null distribution to compute something empirically. Now, before I start the different example, before this the start of this course, I ran a query, a protein sequence alignment. Actually, I ran this one, the DAHO. So the first sequence here, I put it into BLAST. And the reason I did was to show you the different e-values, which are non-zero. Okay, actually, even with percent identities, we have non-zero e-values. The e-value, the smaller it is, the more significant the alignment. And there you see that all these statistical significance values are very small, very close to zero. They are all significant alignments. What I want to show you from here is the BLAST parameters. Let's see where it is. Well, in the previous version of BLAST, it was at the bottom, the additional statistics. It's somewhere probably here. How to read this report. See details, yes, here. So if you look at this details, this is the details of the database, details of the parameters, other report, multiple alignment, align descriptions, graphic summary. Yeah, I think it's maybe, no, this is the graphic summary. Show the alignments themselves are here. So you can see the individual alignments between our query protein and the database protein. And BLAST also, this is the expected value. The bit score is shown here. And I wanted to show you the parameters BLAST used. The lambda, for example. Is it the search side? It's here. Okay, in search summary, we have the search parameters and those, the Carlin, there's a section, there's a table at the end, the Carlin-Altschul statistics, which is the things that we discuss, which is the subject that we discuss on our slide. So if you look at this lambda, you can see what the value of the lambda that they use, the value of K that they use in their statistics. So I think they're using a more advanced version since it's a statistical significance for alignments with gaps. They have other parameters here as well. But this lambda and this K that you see here in the first two rows are the same constants that are on our slides. It's also showing what's the number of total letters here in the database. So the database contains 134 billion letters. So that M in the statistical significance, the size of the database is 134 billion, coming from this many sequences. And there are other things that they use. They use Blossom 62 matrix, the word size. Oh, so they're not using a word of 3 for protein sequences anymore. The word size is 6. So they're first looking for exact matches of 6 amino acids. And they also have a threshold of expected value 0.05. If it's larger than that, they just throw this out. A gap opening penalty of 11 and extension penalty of 100. They look at a hit list of size 100 first and sliding window of a certain size to find these things. So there are different parameters of related to the details of the algorithm. I just wanted to show you that when you look at the search summary, the search parameters database, and you see Carlin-Altschul statistics, these are related to what we have seen here. Okay, so it's actually break time now. Maybe, yeah, let's have a 10-minute break. And after the break, I'm going to just give you another example, statistical significance computation example that I used actually in my research during my postdoc, I think, or I think it was, yeah, it wasn't during my postdoc. I was in a paper. We had to compute. Actually, it was if the statistical significance for the results that our algorithm found, and I'm just going to give you as an example to show you how statistical significance can be computed. All right. So now let me stop the recording.